when we were looking, or where we ended, we looked at chymotrypsin as an enzyme to kind of evaluate when we're thinking about active site chemistry. And one of the things that we mentioned was that serine and histidine were decided to be the critical parts of the enzyme, or active site. And so what we could go through and do is modify, either by changing amino acids, which is a bit of a pain, but we could go through and change each and every single amino acid and see if that affected the protein, or we can go through and label. So what we're talking about with dip and toothpick, as I like to refer to them, is that those covalently link to serine and histidine anywhere that they're found within, or anywhere where they're exposed to the solution. So we could take our protein, throw it into solution, and then add dip and toothpick to it, ideally one at a time. That would then bond to serine if we did dip, and then we could test the activity. Okay? If serine was critical to the chemical reactivity, when I change it by putting on the dip, okay, what happens? I no longer have serine, I can't do any chemical activity. Okay, so we see the enzyme shut down. Same idea happened with toothpick. So we could then, or pull some information without actually getting any kind of structural stuff, that serine and histidine are critical to the enzyme activity. Okay? With some further, I think that was mine. With a little bit of further analysis, they ended up finding out that serine 195 and histidine 57 are critical to the activity. And it's not super important to know those numbers, but the interesting feature about that is that they are not right next to each other. Okay. How could two amino acids not right next to each other be involved in the active site? Remember, your protein can fold up on itself, putting those two amino acids next to each other in the active site. And so if we went through and used X-ray crystallography, we could then get an image of our protein. This just happens to be a cartoon animation of it. And you'll notice they are calling out or labeling nicely, sort of nicely at least, the serine residue and the histidine residue. Notice they also have an aspartate residue. Okay? Aspartate is useful in the mechanism for this, but it wasn't critical to the overall reaction. Okay? How do they know that that is the active site? But if I remove serine 195, how would I remove that? Then I'm now one amino acid shorter. It is targeting a particular sequence, right? Chymotrypsin was trying to cut phenylalanine or tyrosine. What if we built a fake peptide that mimics that? If we build a fake peptide that mimics and then somehow has it covalently bind into that site, when I go through and run X-ray crystallography, I now have that extra little piece stuck in my crystal. I now know that that's the active site because it was targeting that mimic. Okay? Which I think we talked about that with, what was it, the PNP and DADME a while ago. Okay, so drug analogs on targeting different things. It's the same kind of idea here. So what is the kind of biochemistry behind it, or really the organic chemistry happening? So if we look at the first stage of the reaction, that's our upper left-hand corner. We've got histidine, we have our serine, and then we also have our target peptide. So this is our target peptide in here, which is kind of hard to see that it's not connected to anything. But if you look really carefully at each of those edges, it doesn't connect. Is it not in the slides? Oh, I know why it's not in the slides. It is that slide. There's something over the top of it. It is out of the book, I believe, so it's not a huge issue. So we have our target enzyme, we've got the histidine, we've got the serine. They're trying to show some little wavy shapes, those wavy shapes being the parts that are grabbing onto the R groups, quite likely the R group of tyrosine or phenylalanine. Okay, so that's kind of your binding pocket site. the histidine and the serine are then interacting with each other to facilitate the cleavage of that bond. Okay. And what we are referencing when we're talking about the cleavage of the bond is the carboxyl terminal of our phenylalanine. So if we draw, that's close enough. Fine, it's not close enough. Now it's close enough. So we have our phenylalanine. So we're cleaving that carboxyl end, that little red arrow. To break that bond, I need to help polarize and allow that system to split as much as possible. So if we look at the components of that bond, it's a carbon and a nitrogen. Okay? What charge is the carbon likely to be? Positive. Okay? So if I have the nitrogen leave, something needs to replace that nitrogen. Okay? We need an electron source to replace that nitrogen. Okay? The nitrogen, conversely, will need a lack of electrons, a positive thing, to somehow come in and replace the carbon. Okay. Within that whole peptide bond, the weakest link is going to be the carbonyl carbon being the most positive. The nitrogen can't really donate electrons because its electrons are currently being donated via resonance into the peptide bond. Okay. So the carbonyl carbon is the only thing that's potentially positive here. Okay. That is the only reactivity. Which means, what does the peptide or our protein need to supply to help break this bond? Electrons. So we need to find electrons in our protein. We have two choices, histidine and serine. Histidine is a decent base, but is it going to be able to donate electrons into the carbon? This goes all the way back to OChem. As a hint, it's not doing it. So should the histidine be able to share electrons with the carbonyl carbon? Okay, no. So we got that answer, but of course I'll be a jerk and ask, why? Why is that nitrogen not sharing electrons with the carbon? Why are we not seeing this purple arrow?
It's the resonance effect.
If there's a resonance effect, then those electrons on the nitrogen aren't accessible, in which case they wouldn't be picking up a hydrogen. So we have two options here for that nitrogen. One, do the direct attack that we need it to do, or do this weird acid-base thing that it's saying it should do.
Wouldn't the hydrogen be more positive?
So there's an interesting idea. The hydrogen being a larger partial positive than the carbonyl carbon. That's not a bad idea. I would argue there's another really big one, really big option here. And big was an unintentional, useful hint. What is around the nitrogen? The nitrogen from our histidine. A bunch of carbons, right? What do a bunch of carbons have? Electrons. What's around that carbon of our carbonyl? Electrons. What happens when electrons get near electrons? They repel. We have a steric effect here that prevents the nitrogen from acting as a nucleophile. Okay? Which means I just brought in a fun little word. Nucleophile. Our nitrogen is sharing electrons. Okay? It could share the electrons with the carbon, or it could share the electrons with the hydrogen. If it shares them with the carbon, it's defined as a nucleophile. If it shares them with the hydrogen, it's defined as a Bronsted-Lowry base. Okay? So those definitions that you went through, or should have gone through fairly heavily, about labeling nucleophiles, electrophiles, acids, and bases in OChem comes back because that's what explains all of the chemistry going through biochem. Right? And that's what's on that next section, is getting those definitions. Okay? Because we need to be able to look at a reaction and label, what is it doing? Is it acting as a Bronsted-Lowry acid or base? Is it acting as a Lewis acid or base, which is a bit wonky because Lewis kind of covers everything, and we tend to apply electrophile and nucleophile. So our big definition difference, Bronsted-Lowry, we're transferring hydrogen. So we're looking at a proton donor being defined as an acid, and a proton acceptor being a base. We could look at the Lewis acid definition and the Lewis base definition, and yes, this is color-coded. Okay? The issue with looking at the Lewis acid definition, it's an electron acceptor. What does H plus do in a reaction? What do acids react with? They react with, come on. Acids react with bases. In the course of this reaction, what did the H plus do? We could say it donated the proton. We could also have looked at accepting electrons. What's the issue with the Lewis definition? The Lewis definition covers all chemistry. We want to narrow our reference down. Okay? So yes, Lewis is correct. Okay? But if I want to look at an individual reaction, I say, oh, it's acting as a Lewis acid. Okay, what does that mean it did? It could be either reacting with a hydrogen or reacting with something other than hydrogen. So at least from my perspective, it makes sense not to really label things as Lewis acids and bases because that covers virtually everything we could possibly look at. So what we want to do is kind of subdivide that category out, and instead of looking at Lewis acids and bases, we'll look at Bronsted-Lowry, in which case we're referencing the transfer of hydrogen ions, or we can look at nucleophiles and electrophiles, or electrophiles and nucleophiles, which is now the transfer of electrons to something other than hydrogen. We can then be a little bit more clear when we're referencing our reactions. So when we go back up to our reaction here, what is the histidine doing? Well, it is sharing electrons with a hydrogen, meaning the histidine is acting as a base. Because we've differentiated these definitions now, when I say base, I'm referencing very specifically a Bronsted-Lowry base. Okay? And I'm not confusing it with a Lewis base. Okay? What does that mean the serine acted as? And this gets irritating. Stupid biochemists and their useless understanding of arrows. How many electrons would that hydrogen then have around it? Nitrogen just shared electrons with it, so there's 2. What happened to the bond between the oxygen and the hydrogen? Nothing, which means how many electrons are around that hydrogen? 4. Can hydrogen have 4 electrons? No. This is a biochemist not understanding mechanistic arrows and skipping steps. Okay? We officially have those electrons going to the oxygen. Okay? We're also skipping steps here because we've now done an acid-base reaction, which is one mechanistic step. What else are they showing happening? We're also showing that oxygen sharing electrons with a carbon, meaning that species that we just labeled as an acid is now acting as, careful, a nucleophile, because it's sharing its electrons with something other than hydrogen. Okay? A species can be labeled as both, but not in the same mechanistic step. What's happening here? It's ultimately someone getting very lazy with drawing out the reaction because they say, oh, biochemistry doesn't need organic chemistry, so I'm just going to pretend stuff happens. This is why nobody believes that there's organic chemistry in biochem, because they're presenting it in a horrible fashion. They've removed the understanding behind it. Okay? Not that I have strong opinions. Okay? So if the oxygen is then acting as a nucleophile, what does that mean, our peptide? It's acting as an electrophile. That would then exceed the octet on the carbon, so what has to happen? We have to break that pi bond, put it up on the oxygen, forming not really an acid, so I'll accept a charge. So if we look at our product, we do have a charge here. Intermediate is half the word I'm looking, or half the phrase I'm looking for. This goes to the tail end of Chem 230, hopefully, and kind of the whole middle section, Jen, of second semester OChem. What type of reaction occurred here? Okay, and this is hard. What type of reaction happened in the red arrows, not the blue one? The blue one's acid-base. Did I eliminate anything?
No, at the end you did, not in the intermediate.
To go from here to here, what did I do? What did I substitute? I broke a double bond. I broke a double bond. What type of reaction is the breaking of a double bond? Elimination is the formation of a double bond. What is the opposite of elimination? Addition. I'm doing an addition reaction. Okay? It's not a standard addition that we might have remembered from the beginning of OChem. It's towards the end of OChem because what happens later on? The electrons come back down, and we now do the elimination. What mechanism am I doing? An addition-elimination mechanism. In an addition-elimination mechanism, we always form a particular intermediate. That is this structure. It is known as the, oh, look at that. It's on the slide. A tetrahedral intermediate, because the carbon that did the reaction, what's special about its hybridization now as opposed to where it started? The bond angles have changed. We went from 120 to now 109.5. What geometric shape has 109.5 bond angles? Tetrahedral. Okay? So they were intelligent enough when putting together their mechanistic steps to show one of the critical intermediates from organic chemistry. We have the tetrahedral intermediate. They just decided that there's too many mechanistic steps to show, so they're going to ignore doing it properly. Okay? And they jammed it all into one mechanistic step at the front. Okay? Why is the serine oxygen better than the nitrogen of the histidine to act as a nucleophile?
Did you say less sterics?
The easiest answer would just be less sterics, right? We said the histidine couldn't act as a nucleophile because it was sterically hindered. Well, if the serine's acting, it's got to have less sterics. Do you believe that it has less sterics, or are you just saying that? I'm going to assume by silence you're just saying that. What's around the nitrogen? Carbon and carbon. When we remove that hydrogen, what's around the oxygen?
Electrons.
Just lone pair electrons, yes, and then a carbon. I have a negative charge on the oxygen. Do I have a negative charge on the nitrogen ever? No. Which is a better nucleophile, something that's negative or something that's neutral?
Negative.
Negative. Okay. Sterics. 2 carbons around the nitrogen, 1 around the oxygen. Which one has less sterics? The oxygen. Okay. So we can look at the nuances of organic chemistry to explain what is happening in biochem. Okay. This does take us to our tetrahedral intermediate. From the tetrahedral intermediate, we can reform the pi bond, which means our elimination, because now our carbon has exceeded the octet. What do we decide to eliminate? We'll want to eliminate the nitrogen because if we eliminated anything else, it's either 1, a horrible leaving group, or 2, it takes us backwards. Okay, so the nitrogen's really the only option. Would the nitrogen be a good leaving group? Would the nitrogen be a good leaving group? Is that a good leaving group? Why not? It's negatively charged. That's not a good leaving group. Okay? So this reaction does not want to occur. So what does the enzyme have to do? Help it occur. How does it help it occur? I had better not have a negative charge on my leaving group. How do I fix that? Well, histidine just picked up a hydrogen. What can it do with that hydrogen now? donate that to the nitrogen of the peptide backbone. And so again, what are they showing? Whoa! Sorry, wrong eraser. If you notice the arrow that I drew went to the nitrogen, they're showing the electrons going immediately to the bond in place, which is stupid. They should show it go to the hydrogen. Okay, but then hydrogen has too many electrons, and the electrons get kicked back into the histidine. Everybody see it? The result is what happened. What do we have in our product? What's special about the histidine? It's neutral. It went right back to where it started. Cool. Okay. If an enzyme is acting as a catalyst, it had better return to its native state. Okay. So the histidine has returned. Awesome. What happened to the peptide bond? It's broken, which means that amine piece can then float off back out into solution, and we've cleaved the bond. Awesome. That was the other big goal. Where's the serine? It is attached to, yeah. What was this R group?
Is it phenylalanine?
That's the other half of the peptide that we were trying to cut. Do we have serine anymore? No. It is covalently bonded to the peptide we were trying to break. Have we returned to our original enzyme? No. We have to somehow get that piece off. Okay? So what do we end up doing? We still need another hydrogen, just like we had up here, to facilitate all of those transfers. But the issue is we don't have any more hydrogen. We got rid of it to the amine. But we're 70% water. Water can float up into the active site, and water supplies both our hydrogen and an oxygen that can act as a nucleophile to help transfer out the rest of the reaction. You asked me, that's kind of neat. You didn't ask me, but I'm going to tell you anyway.
But that R group is still bonded to it.
What is the R group still bonded to?
The serine.
Okay, so here, you're right. The R group is still bonded up to the serine. Okay, we get the hydrogen from water, so we end up running the reverse of what we did up here. Histidine takes a hydrogen from water. That makes this oxygen from our water a really good nucleophile, so it can attack our carbonyl. That breaks the pi bond. We end up at our tetrahedral intermediate again. The electrons come back in, reform our carbonyl, and kick out the oxygen from our serine. That's a bad leaving group, so what does it do? It immediately picks up the hydrogen from the histidine. So histidine acts as kind of a temporary, here's a hydrogen, I'm going to take a hydrogen. Here's a hydrogen, I'm going to take a hydrogen. Serine is acting as our nucleophile through this process, okay, or base, depending on what we're trying to do. If we then move to the very end, there's serine. The end of your serine is OH. That's just an OH. So serine's back. Histidine, well, that's histidine. What are they showing with the dotted line? Hydrogen bonding. There's a strong hydrogen bonding attraction between the histidine and the serine. If we look at the other half of the peptide bond, is that half of the peptide bond connected to anything, covalently linked to anything? No.
The OH is the serine, not the...
The OH is the tail end of your serine, okay, which they're attempting to kind of show all the way back at the beginning. I can get kind of selective with my eraser here. That's the tail end of your serine residue, is the OH. Okay. Your histidine residue looks like that one. So we have histidine, serine, and then, whoops, the peptide. Okay, coming in.
Is that peptide like free floating in space like the water, or is that already
Yes.
attached?
It is not covalently linked to anything. Okay? So this is one of the things that's kind of important. Your substrate comes in, your substrate does not covalently bind to your enzyme. If it covalently binds to the enzyme, you're screwed. You no longer have active enzyme. Okay? Through the process of running the reaction, yes, we can sometimes see covalent linkages happen, but not always. Depends on what's actually happening. In the case of chymotrypsin, where you're cleaving a very stable bond, we're probably going to have to form covalent linkages because that bond is stable. It doesn't want to break apart. So the enzyme's going to actually have to force that bond to break by covalently linking to it. Yes, the enzyme is inactive. That's why we have to both break it and then release it at a later stage. Okay. So parts that you're responsible for. Okay, we have curved arrows. Okay, the curved arrows show the motion of electrons. Okay. Labeling acids and bases, labeling nucleophiles and electrophiles. You are responsible for that information. Okay. Relatively minor right now. The next unit, when we're looking at metabolic processes, that's all we do, is just go through and look at reactions. What's the curved arrows? How do these things break? Nucleophiles, electrophiles, acids, bases, all that fun stuff. Okay? So start reviewing that content now to kind of build you up so that you're set. Yes?
When you say like with labeling acids and bases, is it gonna be kind of both Lewis and Bronsted-Lowry? Or are you gonna kind of want us to?
So what do we say about the Lewis?
It encompasses all versus the Bronsted-Lowry is a little more specific.
Okay, so if Lewis encompasses all, I don't want you to use Lewis because that's now too vague. I don't know that you know what the definitions of those things are. Okay, so what I expect you to go through and use are your Bronsted-Lowry definitions, and then if it's not a Bronsted-Lowry acid and base, it's a nucleophile or electrophile and nucleophile. Okay. What is that key difference? Hydrogen. Bronsted-Lowry looks at the transfer of a hydrogen ion. Electrophile, nucleophile, anything other than hydrogen. Okay? So let's see if I can just pull one out of here. Yeah, let's do this. We just looked at the center one and trying to label what happened. Okay, I'll add them over in purple. That curved arrow, we can't really label. Okay, that arrow is all happening within the structure. If it's happening within the structure, we don't have two things, we have one thing. You can get all sorts of weird labeling that, it's not a good idea. Okay, what about the next curved arrow? Okay, if that is an electrophile, you're saying that that nitrogen is accepting electrons. Or that the carbon is accepting electrons with that arrow. Are either of those accepting electrons? No. We're saying the electrons in that bond are being shared somewhere else. So if anything, that's a nucleophile. Okay? Where are those electrons being shared? With what atom? They're being shared with hydrogen, which means it's not a nucleophile because the nucleophile is transferring to something other than hydrogen. So that is then going to be a proton acceptor, meaning that nitrogen is acting as a base, an electron donor, okay, which would be our base, or a proton acceptor. What about the next arrow?
Wait a second, I need some
What do bases react with?
acids.
So what type of reaction happened there? So acid-base reaction. Okay. Did a bunch of other nasty stuff, and that's kind of irritating. That's because they've jammed too many things into one reaction.
How is that a base when it's donating?
What is the definition of a base?
Proton acceptor.
Okay. What is it donating? Electrons. There's our issue. Protons are positive, electrons are negative. what does a proton acceptor do? It accepts H+. So what does it have to supply to that? It has to supply electrons. So a proton acceptor is an electron donor by definition. Right?
So
Because
can
by
we lump those two together?
yes, that's why when we look at our that's why Lewis applies to all of them. A proton donor is accepting electrons. It's H+ is accepting electrons. What is a proton donor? H+. Okay? So the Lewis definition encompasses all reactions, or all, what is it, I don't know how to end that word, but hetero something, reactions. Okay? Because it applies to all of them, we want to get a little bit more refined because we can reference acid-base reactions differently than we can nucleophile-electrophile reactions. Okay? Does that kind of make sense? And so this is one of the things that's kind of nice about the Lewis definition is it does apply to everything. Which means if you know either your Bronsted-Lowry definition or your Lewis definition, you can find all the others. Give me an example of an acid. HCl. You know that's an acid, right? What happens when you add acid to water? What do you get? Yes, it dissociates, but let's actually do the reactions, the chemical reactions. I wrote two things. I would get H3O plus and Cl minus. You said HCl was an acid. What happened to it in the course of this reaction? It donated a proton. There's your Bronsted-Lowry. Okay? What else could we look at it doing? Okay, for it to donate that proton, well, what did this species have to do? What did our H2O have to do? It had to accept that proton. But how could it accept that proton? It had to donate electrons. Okay? So coming up with just a simple acid-base equation, you can look at or derive all of your terms that come out of it. Okay? Make sense? Okay. Last little part that gets kind of quick that we'll come back to, at least the NAD plus and NADH. There are non-protein molecules that are involved in enzymatic reactions. Right? Those non-protein molecules are usually used to transfer something. Okay? It can be as simple as electrons. It can be as simple or as complex as large units from one location to another. Okay? NAD plus and NADH we will see a lot of because what does NAD plus and NADH transfer? So I heard hydrogen. Yeah, we're going from NAD plus to NADH. And you say, oh, well, there's a hydrogen there. It's not really transferring the hydrogen per se. It's transferring hydride, which is really a fancy way of saying it's transferring electrons. What can we do with extra electrons? Well, we can move into the ETC, our electron transport chain, which is how we get almost all of the energy that we deal with in metabolism. So NADH is a critical coenzyme because that's really where we're getting all of our energy from. Okay? It transfers the electrons, which gets us into a situation where we can now make a molecule that can transfer our energy well. Okay? Your B6 vitamins transfer amino groups. So you've got tons of different variations of them. And all they're really trying to do is take a nitrogen from one location and put it on to a different location. So they can facilitate that transfer based off of their structure. So if you look at all those pieces are very similar. And all of your B vitamins have some aspect of that because they're aiming at that amino transfer. Okay? How does it do that? That's a good question. Do you really want an answer to that? Thank you. I don't have the answer to that. But if you wanted it, I could look it up. Okay? So it's just important to realize that there are these other things that are necessary for an enzyme to function, can be necessary for an enzyme to function. Okay? Questions about that? Okay. Oh, for our B6, the transfer of the amino sometimes gets referred to as transamination. That's all that's saying there at the bottom. And then our transfer of electrons. What reactions transfer electrons? Reduction and oxidation. So NADH, or the NAD plus NADH couple, is a redox mediator because it's transferring electrons around. I don't know why I decided that was an extra thing to add, but there it was. We then jump up to 16, right, as far as our chapter sequence goes, which gets us into carbohydrates. Right? It's a super exciting one if you liked nomenclature. Anybody like nomenclature and like Gen Chem and OChem? Okay. You probably didn't like it the first time, but then you learned it and you're like, oh, this is easy, I just follow the rules, right? Okay. At least that's my general interpretation of it. If you thought the nomenclature system made no sense in Gen Chem or OChem, that's because you haven't seen the Biochem system for nomenclature. Right? If you want to talk about arbitrarily making stuff up, welcome to Biochem. Okay? What we're referencing is our carbohydrates. So a first thing to come up with is how do we reference or look at these? Okay? So our carbohydrates can be referred to as monosaccharides. The saccharide is just saying kind of a single repeating unit, and that is going to be our monomer. Carbohydrates can be a linkage of several saccharides, so we end up with polysaccharides. Okay? So what is a monosaccharide? Okay, well, we fall under the general formula, which I have yet to memorize, so I don't expect you to. CnH2nOn. So we've got an equal amount of carbons and oxygens, and then we have twice the amount in hydrogens. Okay? N can vary anywhere from 3 to 8. Could it vary more than that? Yes, but it's not biological, so we don't worry about it. Okay? Can it be under that? Well, theoretically, yes, but now it's such a small molecule that the chemistry doesn't apply appropriately, and we can't use that biologically either. Okay? So we're really looking at 3 carbons up to 8 carbons. Okay? Within that, we get reference to what's known as aldoses and ketoses. The ose is kind of in reference to the carbohydrate. What is the ald in reference to? Aldehyde. So we've got some sense coming out of this at least, as opposed to nonsense. Huh. I thought that was funny. Ketoses, you're looking at a ketone. So somehow in the formation, to match that formula, we have 1 degree of unsaturation as either an aldehyde or as a ketone. Okay? And that's where our aldose name comes from, or our ketose name. Okay? You guys remember degrees of unsaturation? Not a big deal. Don't stress about it. A degree of unsaturation is equal to a pi bond or a ring. Okay? So fully saturated, a carbon chain should be CnH2n plus 2. Okay? Those of you taking MCAT, you might want to remember that. Okay? Your degrees of unsaturation might pop up on you there. Okay? Other people, probably not. Okay? Because we're at only 2n, we're missing 2 hydrogens. Well, why are we missing 2 hydrogens? We brought in a pi bond, or we brought in a ring. Okay? So if we bring it in as a pi bond, that pi bond will happen between a carbon and an oxygen, and it will be either an aldehyde because that pi bond is happening at the I know that was a really vague statement. Oxygen, 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 right? So there's our 3 carbons, there's our 3 oxygens. Let's not worry about the hydrogens. This is an aldose. Where does our pi bond to an oxygen happen? Which one of those? The end. Which end? Doesn't matter. Man. Well, you probably knew that just because ask questions like that. Doesn't matter which end we pick. Okay? So our aldehyde is now there. So we now have an example of an aldose if we then backfilled with hydrogens. What if we wanted the ketose? It has to go off of the middle, and we backfill with our hydrogens. We now have a ketose. Okay? Your polymer is really where our carbohydrates are, and that's where we now attach multiple saccharides. You can come up with different names for this. If you want to get really annoying, polyhydroxyaldehyde or polyhydroxyketones. Don't stress on that part. Okay? But a carbohydrate or a polymer is a polymer of our polysaccharides or of our saccharides. Okay? So let's start with the simplest chain. What happens if we have 3 carbons? Okay. There are 2 possible results. I get either the aldehyde one, so this is the aldose, or I get the ketose. Okay? But this had 3 carbons, so I want to add an extra bit of information here, and instead of saying it's a 3-carbon aldose or a 3-carbon ketose, I want to condense that in, and I want to use a Greek prefix, and I can call this a triose in both cases. Okay. And I think we'd go keto triose or aldo triose. Okay. So you're just stringing in those prefixes to add more information about which carbohydrate you're looking at. So in this case, we're looking at our trioses. Okay. This is where things get fun, because that at least made sense. We had aldose, we had triose. Okay. But now we want to go through and name each of those pieces. Okay. Well, how many carbons were in this one? 3 carbons. So that would be what root? Prop, thinking back to organic chemistry. So we have a prop. What is our primary functional group? An aldehyde. So we'd have, we could do propylaldehyde or propanal. Do we have other substituent? Whoops, I wrote it in the wrong one. Sorry. I have 2 alcohol groups. So those get diol works if all is the subscript or suffix. We can't do the all because it's a lower priority than our aldehyde. Okay, so we can't use diol. We end up having to name it as a hydroxy. And it becomes, whoops, I left off the dihydroxy, but where are the hydroxys located? Position 2 and 3, we get 2,3-dihydroxypropanol, also known as, oh, clearly, glyceraldehyde. Okay, that makes so much sense. Okay, well, let's just accept that and move on. What about the other one? Okay, well, now I have a ketone, still 3 carbons, so it would be propanone. We have 1,3-dihydroxypropanone. Okay, well, we learned nomenclature for a reason. That's useful. We can get those names. And yet we call it dihydroxyacetone. I would at least argue that one somewhat makes sense, because we're saying dihydroxy, 2 alcohols, yeah. And then acetone, propanone, acetone, what's going on with that? What is the name of that molecule? Acetone. So, I mean, it's the common name, okay? And common names were super irritating to memorize, but at least there's some sense behind that. Why do we call it glyceraldehyde? If we get rid of the carbonyl, it becomes a molecule known as glycerol. But it's now not glycerol because it has an aldehyde, so we'll call it glyceraldehyde. So it's another common name derivative. Okay? And you probably remember back in OChem when we talked about common names, you're like, oh, that's just irritating, I just have to memorize it. Yeah, you do. Okay? These two molecules are incredibly important to our metabolic pathways. We do need to recognize those names and tie them back to their structures. Okay. Does anybody see anything interesting about either of those two molecules? If we ignore the names. What do you mean cis and trans?
Just kind of how the directions of the hydroxyls, like one.
So I put the OH up here. What's different about that structure versus where it was before?
Less there.
What did I do to get to this position? I did a rotation about this bond. What kind of bond was that? A single bond or a sigma bond, and what can we do with single or sigma bonds? Freely rotate. So that does not allow for a cis-trans because I get free rotation. I'm allowed to do that. Okay? So it's not a bad idea, but unfortunately, no. RNS. Everybody's favorite. We're looking at chiral atoms. So when we look at that carbon, that's a chiral atom, right? No, because two hydrogens. So that's not a chiral atom. So what are you talking about, Jen? Because that doesn't make sense to me.
Doesn't RNS have to do with chiral atoms?
Well, maybe it's that one.
That's not a chiral atom.
Maybe it's that one. Okay. Well, your theory's looking kind of crappy. Sorry. How about that one? How about that one?
But the middle one is.
Oh, look at that. What's that middle one? That middle one is chiral. Which then means we aren't looking at two possible trioses. We have three, where we have two glyceraldehydes that are enantiomers of each other. Okay. The dihydroxyacetone, we don't have to worry about. There's only one, because there's no chiral atom. Okay. That chiral atom becomes important because what are we? We're all biological systems. Chiral, which means glyceraldehyde's chirality is going to become important for how we can process and manipulate it. Okay? So that was just the triose. What happens if we moved up to 4 carbons? What would we call that one? We could do bute, but that's too much like organic chemistry. And remember, biochemists don't like organic chemistry, so we can't use a similar nomenclature system. What's another way to reference 4? Quad's not a bad idea, but no. Tetra. We can get to tetraose. What if we had 5 carbons? Pentose, 6 carbons. Hexose, 7 carbons. Heptose. Okay, 8 carbons, because we had 8 octose. Okay? In each of those cases, what do we end up getting? We also get aldoses and ketoses. But what happens if I add an extra carbon to this? If I add another carbon out here with another OH, as Jen just suggested, I have the original chiral atom and another. Add another carbon. And another. And another. Which means when we scale up to more and more carbons, we don't get just 2 or 3 possible orientations. We get a crap ton. Okay? This is where biochemistry nomenclature becomes an awful mess. But yes. You said, but wait, yeah.
Oh, no.
No. Okay. So what happens if we have chirality? This is where we have that whole R and S. You remember how to do R and S?
Priorities.
You take your priorities. So if we took a look at these two structures up here, okay, we look at our chiral atom. We go out to an oxygen. We go out to a carbon. We go out to a carbon and hydrogen, which has the highest priority. The oxygen, which has the lowest priority. Hydrogen 4, which has a higher priority, carbon or carbon?
Depends on what it's attached to.
Depends on what it's connected to. Okay, well, one carbon goes out to an oxygen, the other carbon goes out to an oxygen.
It has 2 oxygens.
Okay, what you may vaguely remember from your RNS is if you have a pi bond, we have a ghost. That's not a good way to draw a ghost. A ghost. Now it looks very ghostly, probably. I'm attempting to... We have a ghost oxygen, so that carbon is technically bound to 2 oxygens, not 1, which then makes it a higher priority. Please don't lose connection. And so we'd have 2 and 3. If we go through and look, that's going clockwise. This one would be R. If that one's R, what's the other one? S. Okay. That was a little bit of work, but that wasn't too bad. Why does this become 1, 2, 3, 4, 5, 6? Why does this become irritating as we move through our carbohydrates? Now you have a whole lot more R and S to assign. Okay? This is typically where students screw up in OChem, because you go through and you do R and S. You go, oh, I totally know how to do R and S. Okay? You say, oh, I got the answer right. It's a 50-50 shot. Okay? More than likely, you screwed up in your first attempt, but because you got 50-50 coin toss right, you're like, oh, I'm perfect at this, and you move on to the next one. And you get perfect at that one, and you're perfect at that one. And then you hit the exam, and now all of a sudden things go sideways, and now you get the wrong streak. Okay? You need to know exactly how to assign R and S. Shortcuts I highly do not recommend. People use them. If you can use it consistently and consistently get it right, by all means, have fun, do it. Okay? I can't. I have to go through that painful process that we just went through. Okay? So when we move to something like this, that's a lot of extra work to go through and assign. Okay? A guy named Fischer said the same thing. That's way too much work. Okay? So I want to remove or simplify my structure so that I can assign R and S easier. Which we did start to talk about Fischer earlier in the semester, right? Right? So highest priority carbon must be at the top. Carbon chain written vertically underneath it, and it's always organized away from you. Bonds to the left or right are always coming at you. And then we can assign D and L. We end up skipping R and S. Okay? If your alcohol is on the right, it is D. If your alcohol is on the left, it is L. What do we mean? Whoops. Let's real quickly take this one. So I'm going to grab this carbon. This is great because you can envision what I'm doing here. I'm going to pull this upwards and kind of rotate this thing down and around. So I have the carbonyl now up. This is now my 3 carbons. Okay. I really only have 1 chiral atom, so it's that middle carbon that's going to become important. As I did that rotation, I'm viewing kind of from the top. Or I could pretend I'm looking at it from the top. If we rotated this down, then we don't really care what this is, that OH. Okay, yeah, I was waiting for someone to complain about that. I'm going to have to do it slower. That's not your fault, by the way.
Sorry.
Of course, I got it too close to all that. OH. Everybody see that? That's all I did. Except I think I had this one aimed that way. Now what I'm going to do is grab this OH, and I'm going to pull it out of the board at you and rotate it over to the right-hand side. The result of that is that my carbon chain is now from that carbon aimed away from it. So the carbonyl is up here. Where's the OH? The right or left-hand side. So I grabbed this OH and I pulled it out of the board over here. It's on the right-hand side. Oof, that was pretty ugly. That's an OH. This is an H. What's down at the bottom? CH2OH. There's an extra carbon there. Why am I not showing that CH2OH on a wedge or a dash? It's not a chiral atom. The only ones I'm really concerned about being on that vertical axis with the wedges are chiral atoms. So the other way I can look at that molecule is because I'm now assumed in the Fischer projection. Can I erase the red one? Is that a no?
I don't get why you put it on the other side.
So all I'm trying to do, so the point of Fischer is that your carbon chain must be written on the vertical axis. So we're kind of on the vertical axis, but it's zigzagged. So make it a spine. It's got to be straight up and down. So I've got to turn that out. Okay? And then by definition, the carbon chain must always be away from your carbon. So if that's my carbon that I'm staring at, this carbon chain must be away from you. Okay? So that's why I have to pull the OH out, because if I push the OH back, where's this carbon chain then going to be aimed? At you. Because what we've got is that, right? So if I pushed the OH backwards, the carbon chain's, wow, that's hurting my hand, is aimed, wedged at you, and it needs to be dashed. So if I'm here, the OH needs to now be pulled out so that the carbon chain, my index and middle fingers, are aimed away from you.
But doesn't the solid line mean that it's coming at you anyways?
The wedge means it's coming at you, yes. What's happening to the hydrogen in back? It's dashed going away. Okay? This format in and of itself isn't a problem until I add a whole bunch more chiral atoms. That then becomes difficult to go through and assign. And it's easier to look at it in the Fischer projection. Okay? So, and that's what we'll look at in the next example here. Because what I've shown so far, you're like, well, why would I bother to go through all that trouble? And I understand. Why would you bother? Typically, when you're in OChem, you're only looking at one chiral atom, maybe two. It's not that big of a deal to go through and just assign R and S. When we move into biochem, however, we have a whole lot more than just one. Okay? So Fischer then simplifies this down, and actually simplifies it even further down into this representation, CHO. We've got our aldehyde, we've got the cross, the OH is on the right-hand side, the hydrogen's on the left, the CH2OH is on the bottom. Notice I'm now using solid lines all the way around. And as you just suggested, solid lines imply what?
They're in a plane.
They're all in the plane. Can I possibly have all of those bonds be in the plane? No. This is where Fischer came in and said, if you've done what I told you to do, that's what Fischer says, okay? You are now looking at it in this format, which means every bond on the vertical axis is going away from you. Every bond on the horizontal axis is coming towards you. Okay? Which means, well, let's simplify. If that is by definition the case, then I don't need to show that they're all going away. I don't need to show that they're all coming at me, because that's how I've defined the system. I can now simplify that down into this format. This is why biochemists say there's no OChem. They say, oh, there's no wedges and dashes. Because jerk off, somebody already went through and fixed it for you. Okay? Yes, there are wedges and dashes. Okay? You've just ignored the fact that they were done for you. Okay? Kind of makes sense? I'm not calling you guys jerk offs, by the way. Okay? So we have to be able to recognize how we can move into that and ultimately do our interpretations from the Fischer. Because your background is in the OChem side of it, we have to do that transition across. This is that transition. Okay? And I'm trying to drag you without kicking and screaming. Okay? Once we're here, we now have some simplifications that can make life a little bit easier. Where's the OH? On the left or right-hand side of the structure? The right. So I can now refer to this as D-glyceraldehyde, because the OH is on the right-hand side. Okay? What if I'd done the other one? The OH would show up on the left-hand side, so I'll call it L-glyceraldehyde. Okay? So then notice again, we had R and S before, not D and L. Two separate systems. Okay? If you remember back to OChem, and it may depend on the level, you had optical activity. Is that ringing any bells? In optical activity, you had D and L there, right? How was D and L written for optical activity? How is it written, the symbol? Lowercase d and L, not capital D and L. An entirely different system. Okay? So there's really three ways we can label chirality. R and S, looking at structure. Lowercase d and L, or plus and minus, which is experimental. And then capital D and L, because the other two methods weren't good enough for biochemists. Probably because Fischer just covered it all at the same time as everybody else, and then nobody just agreed. Okay? So what does that mean for us? Well, what happens if we scale up to a more difficult structure? Okay. If we look at this compound, that's 4 chiral atoms. That's a lot to go through and assign all this R and S stuff to. So this is where Fischer says, I don't want to deal with wedges and dashes anymore. Don't make me. So I'm going to go through and organize my format, put it on the vertical axis, my carbon backbone. Notice my highest priority carbon is at top. Okay. I then need to take that structure, pull it out of the plane. Okay. And this is where Anna might make up her point again. Do I have to pull it out towards the right? Couldn't I have pushed it backwards? Yeah, unfortunately, when we have more than one chiral atom, yes, because that's going to bring up the next issue. When I pull it out, and I'm pretty sure I pulled it to the right, yep, what happens on the carbon backbone? Is it aimed always away from you? No. What does that mean has to happen? You have to go through and evaluate each of those with typically with the models, the easiest way to do it, and you'll notice that this one, if I'm looking from this side, is perfectly aligned. How about the next carbon? No, so what do I have to do? I do a sigma rotation to get that lined up. The next one would be aligned. The next one's not aligned. I do a sigma rotation. So I end up rotating these when they aren't aligned to get me into this format. That's now effectively my Fischer projection, and you look super excited about that. All right? Look what happened. The first one was already set up perfectly.
But how do you know that?
What's our rules? Orient the carbon chain vertical axis, yes. Okay, highest priority carbon at top, yes. Substituents, vertical axis and aimed away. For this first carbon, are those the carbon chain aimed away? Yes. How about the next one? No. That one's not oriented right. So what I will do is rotate about that bond. In the process of rotating about that bond, where does the OH then slide? It has to switch to the other side. Yeah, it's freaking mind-bending.
How do you know that carbon isn't aimed away? Because the OH is
Your zigzag here. So when we're looking at from this side, and I'm looking at that carbon, where's the backbone aimed? It's aimed away. I can't now say, well, I'm going to move over to this side. Okay, that doesn't work. Okay? If you were trying to draw a person and you drew the left side of their face, and you're saying, well, now I'm going to draw the right side of your face, but I'm going to draw from the back side. You're going to draw a really weird-looking face. Okay? So you have to maintain the same orientation. The issue is that when we get to this carbon, where's the backbone aimed if I'm looking from the left? It's coming at you. Okay? So it's a visualization issue dealing with organic models. And depending on how much that gets pushed in your OChem class, you may or may not recognize where those arrangements are coming from.
So you know the carbon going away because the OH is coming out. Because that
No. Oh, okay, there we go. There's our issue. Let's draw on an eyeball. There's an eyeball. Nice little pupil. See? It's even got a little glow. Eyelashes. Some little kind of veiny stuff. Okay, so we're looking at this direction. Okay? If I'm looking at it that direction, where's this line and this line aimed?
Okay.
Away. If we now shift our eyeball down just a little bit, where's this line and this line aimed? Towards you. That doesn't match. In Fischer's rule, it must be aimed away from you. And part of this that gets confusing is that we go through and do this. And you say, oh, finally, let's just accept that it's happening. Fine, Mike, just do it. Right, there's our structure. We could simplify that down by just showing all of it as the crosses. What would the actual model look like if we did that? It's going to spiral back on itself. Okay? And I attempted to show the perspective here. I don't know if you can recognize that or acknowledge how awesome that was. Really, really big, and look what's happening to the bonds and the atoms as we continue to move around. It's progressively getting smaller, right? So we're showing the perspective of it spiraling away from you. Okay? Build a model for any one of your carbohydrates and try to orient it in the Fischer view. What you'll find is as you do each of those rotations, you will have spun the molecule into a spiral. Which is kind of neat and scary all at the same time. Okay? And so what Fischer is doing is individually looking at each carbon and now changing his perspective, which then means as he draws it out, he's rotating the molecule around. The only way that you can get all those bonds aimed away from you is by cycling around the structure. Okay? So what do you think this carbohydrate would be called? Stupid. Okay, I heard D. But isn't that on the left-hand side? What is our DL system referring to? The last chiral atom in the chain. The last chiral atom in the chain is this one. This carbohydrate is known as a D carbohydrate because where's our highest priority group? In that last one. It's on the right-hand side. That's why it's a D. We don't care about the orientation of the other ones when referencing D and L. That was right about when I gave up on biochem nomenclature, by the way. You said, this is stupid. Okay. Up to you. That's your points. I accepted point loss. I accept point loss right and left. Okay. Your D and L is only referring to that last carbon. So how do we know how to organize those for an individual molecule? Okay. Well, how did they go through and do it? If we look at a 4-carbon chain, this is D-erythros and D-threose, because when we look at that last chiral atom, where's the OH? On the right-hand side. This D-erythros, though, has the OH on the right-hand side at 2, and this one still has an OH at carbon number 2, and yet what do we call it? Threose. How do we know the OH at carbon number 2 for threose should be on the left? Because it's called threose. Yeah. So what happens if we made this L-threose? That OH that's specifying it as D must be on the left-hand side. What happens to the OH at position 2? Stays the same because that's what makes it threose. Yes, I completely agree with you. Okay. This will bring in this issue of mirror images, okay, with your erythros and your threose and all that fun stuff that we've got to worry about. Okay. So we have to compare enantiomers, diastereomers, and nasty stuff. So what happens when we scale up to larger structures? Well, then you get these, well, if we only have one chiral atom, it's known as glycero. If you have 2 carbon atoms, it's known as erythro. Okay? 2 carbon atoms, but they're on opposite sides. They're threo. Yeah. 3 chiral atoms. We get arabino. Mother of God. Okay? Yes, this is where our organic or biochem nomenclature for our carbohydrates just turns into a mess. How much of that you're responsible for? Virtually none of that. What I expect you to be able to do is identify D and L. That's pretty much it. Okay, at this point, because we're going to bring in another one. Okay. Notice with these are all pretty much, actually they aren't even all referencing that. Okay. If we scale this out, we look at the aldose family tree. As we add carbons, each of those letters corresponds to a different name. That's awesome. This, by the way, is the aldose family tree, meaning there's a ketose. Okay? What is extra fun with the ketose? Where can a ketone show up? Anywhere in the carbon backbone. If I have lots of carbon backbones, I get lots of variations of the ketose. Okay? So what I want you to be aware of is kind of the scale of this nomenclature system. That's ultimately where it's coming from. A biochemist would just look up the freaking names. Okay? If they were using that carbohydrate frequently enough, they would have it memorized. Okay? Do you think any of those would be particularly important to memorize? I think I heard it. What was it? Gluco because glucose. There's another big important one. Ribo because of ribose, ribonucleic acids. Okay? So knowing what a ribose sugar looks like and what a glucose sugar looks like will be important. You should memorize those. The rest, put them where they belong. Okay. Remember what we looked at? We said it cycled back on itself. What is special about the aldehyde carbon? It is the highest priority, yeah. There's a pi bond. What's special about pi bonds in comparison to sigma bonds? Pi bonds are not stronger. It's a common misconception. Double bonds are stronger than single bonds. A pi bond is not a double bond. A pi bond is an extra single bond on top of a single bond. So a pi bond is actually weaker. If I have a weak bond, what could it do? Break. How is it going to break? Where are the electrons in that pi bond going to go? To the oxygen or the carbon? The oxygen, because more electronegative, which means the oxygen becomes negative, the carbon becomes positive. Does carbon want to be positive? What would it need? Electrons. Does there happen to be a sequence of electron source somewhere now nearby because of this stupid Fischer projection? Yes. What happens with these nice straight chain carbohydrates? Almost always they double back on themselves and they cyclize. We form cyclic structures, which then means we have to refer to them by their new names. And we end up with hemiacetals and hemiketals, both of which should have been addressed in both the 230 and the 235. Ketals and acetals, 230 people, and I need to look. I'm seeing some no's. Okay. So we'll address that. If we cyclize carbon number 1 to carbon number 5, carbon number 1 then means our aldehyde, our carbonyl was an aldehyde. That's going to be referred to as an acetal because acetal begins with A, and our carbonyl, if it's a carbon number 1, is aldehyde, which begins with A. What if it was carbon number 2? Well, then our carbonyl would not be an aldehyde, it would be a ketone. So it'll form a ketal. Okay? 5-membered rings, pyrans, 6-membered rings, furans. Okay? Why? Germans? I don't know. Okay? Why do we not see 4-membered rings or 7-membered rings?
The bond.
They're not as stable. Your 5-membered and your 6-membered rings form the most stable rings. That's where we get our pyranoses and our furanoses. Okay? I just want to mention here, because I want you guys to look at it over the weekend, I will ask questions about D and L, because we've addressed that with our carbohydrates. We'll look at kind of a lot of that nomenclature aspect. The other big part of it is your alpha versus beta, okay? Which, if you didn't like D and L, I apologize, alpha and beta are pretty much the same kind of funness, okay? So review that, try and figure it out. I've got slides that summarize it. After that, it's pretty much just a bunch of memorization from your carbohydrates. Okay? That will show up on the exam. Okay? To a more limited extent, because we didn't explicitly talk about it, but all I'll be doing is saying, well, this is this one, well, this is this one. That's it. Okay? So review the slides, show up Tuesday with questions, you should be good to go. I will also say I am insanely highly stressed and insanely highly behind on everything in my life right now. You can kind of take that to mean stuff.
Thursday's the